previous example of TERAC, the radiation machine TERAC 25, it was more catastrophic because in the previous one, people are passed away. Here, okay, so it's about money, but when it comes to people, to human life, of course, human life are more like costly, let's say, if you want. So to finish with examples, I want to finish with a newest one, let's say, or with one that happens in recent years, because the previous it was in previous decades. Here, Log4j bug is also very famous and very known bug in the most recent, as I told you, years. It's Log4j vulnerability, and it was discovered in 2021. This vulnerability, if you want, it affects millions of websites because millions of websites use this library. It's a very known library, Log4j library, and it's a common Java-based logging utility, and it's used by companies around the world. And then, so this vulnerability it allowed hackers to execute code on web servers remotely, which is catastrophic, also leading to a widespread potential for cyber attacks. Many attacks that happened due to this library that was used by users. And then also it's considered as one of the the most known bugs and failures. And so vulnerability, the difference between vulnerability and bug. Vulnerability, when we talk more about when it comes to security, when it comes to attack from hackers, but also at the end, it's a bug that was that is in the code that make it as vulnerability, which we make here the code vulnerable. It means that it's insecure at the end. Here the idea of automated program repair process. At the end, a lot of bugs that appeared and happens in the code that we can find in the code, even with exhaustive testing. As you know, exhaustive testing is very difficult. It costs a lot. It's very complex to do exhaustive, but with different strategies of this, we still enable to remove all bugs, to detect all bugs, to localize all bugs. So it's a real problem that need to take it in consideration. For that, an APR or automated program repair process, it was defined and it was implemented to help developers and software quality assurance engineer to detect those bugs and to fix and to repair those bugs. So as you can see here in the process, the first part is about fault localization, which is the initial step, which involves identifying the part where exactly in the program the error occurs. It's very important to localize that error. It's the process that starts with a buggy program, a program that is not clean, that it contains bugs, that has some failing tests indicating issues. So for that, it's a buggy program. And then using various fault localization tools, the specific part of the code that are most likely responsible for the bugs are defined or are determined. So the output at the end is a ranked list of suspicious code locations, prioritizing where the fixes might be needed. So this is the first part of the process. which we have to localize the fault. The second part is patch generation. So the potential faulty area are identified, are localized in the first part, in the fault localization. The next step, so, is to generate possible fixes or patches. This is what we mean by patch generations. Means we will create several candidates. And this involves using, of course, our automated program repair process or approach, which can vary in methodology, but generally includes techniques like template-based. It's very known technique to create several patch candidates. Genetic programming also widely used today in different areas. And also, so it's used today to fix, to patch generation or to fix bugs and to define quantities. This one that we will explain it and we will use it today. So the idea is, again, generate multiple patch candidates and which are potential code modifications meant to fix identified faults. And the last part of the process is patch validation. So it's the final step, as I told you, which is to test this patch candidates that was generated in the second step of patch generations to see if they actually fix the bugs without introducing new ones. So each candidate patch is applied to the original program, and the program is retested more than one time. If the patch passes all tests, including the previously failing ones, it's considered a good patch and can be adapted as a correct fix. If it fails otherwise, so if it fails, it's discarded and the next candidate is tested until we end up with the good candidate and the best solution. Move on, as you understand that our first step in the process is about detecting bugs, uh, and we must scan our code to find where things go wrong. We have to localize our bugs. This is the first step. Here we have the fault localization phase, which is very important and crucial for efficiency, identifying which part of the program are likely to contain bugs, which can help developers to fix the bug, right? One of the very known technique used today is spectrum-based fault localization. So to explain this technique, this technique it uses the execution traces. We have to execute the traces of passing and failing test cases. So as you can see here, our first and initial component test cases, here it will be used and we will run our test cases. So test suite is a set of test cases. We will run test case per test case, one by one, and we will check each time if the test case passed or failed, to check at the end to end up to be able to identify the problematic code, the part of the code that is problematic. And by analyzing which part of the code are executed during failures versus successes, spectrum-based fault localization assigns scores at the end to different segments, indicating the likelihood of containing a fault. So each time we run, our test cases are already well defined. We will run them one by one to check if one of them will fail, will not pass, means that here we have a problem, and then means that in this part, of course, as I told you, it's about execution of traces. So we will identify the part of the code that it's not it's not clean, let's say. So here our two inputs, our test suite and our program, our initial program that it's initially will be tested. It's being tested. It's subjected to the test suite to ensure if it operates correctly and to identify any areas that may not function as intended. This is spectrum here. It refers to the spectrum of execution traces collected from running the test suite, test case per test case in the program. So it's essentially, it captures which parts of the program code are executing during the tests. And this data is very important for analyzing the behavior of the program under various test conditions using different test suites. So using the data from the spectrum, here, as you see here, this formula calculates the risk associated with different parts of the program. It evaluates how likely each part is to cause failures or problems based on its performance and during the test suite executions. And at the end, we have here the risk value ranking. It's the output of the risk evaluation formula is a ranking of different parts. So we have ranking at the end as output of the program based on the calculated risk values. This ranking helps identify which areas of the program are most problematic or risky, allowing developers to prioritize fixes or even further investigations if needed. This is so the first part about detecting, which we have to run our test cases, to execute traces and to check, and then to rank our components. The second step here, once we have detected the issues, the bugs, our next step is equally important, is important as detecting bugs, which is fixing them, of course. So fixing a bug involves understanding why we have that bug, how the error occurred, and then applying the right solutions to ensure it doesn't happen again, which is very important. And the validation part in this stage, so different, sorry, the patch generation part, different techniques here are used to generate like potential fixes or patches for the errors identified in the fault localization stage. So these patches are created based on the ranked list of the previous output that we have, suspicious code locations, aiming to modify the program code so that all tests will pass. So here the idea is that we'll create not only one candidate, we will create several candidates, we will use genetic programming later on. We will talk about mutants. So several mutants, several candidates that will be checked later on, that will be checked in the last part, in the patch validations. So here each generated patch is then tested. Not only one patch, as I told you, several candidates, several patches. So each one is tested to see if it actually resolves the bugs without introducing new errors. You have to be careful about the patch generation because there is a high risk when you fix something, other thing else will be affected directly or indirectly. So you have to be careful about this and you have to check it. So for that, you have also to think about checking the whole system, not only a specific part, because if you don't check the whole system, maybe a new error, it's affected indirectly. And this involves applying the patch to the program and running all tests again. So if the program passes all the tests with the patch applied, means the patch is considered successful. If not, the patch fails and either another candidate is tested or the patch generation stage is, let's say, revisited to create different new patches. This is the whole process. Now let's talk about how we can create candidates, how we can create several mutants. So we can, as I told you previously, genetic algorithm is widely used in this stage of creating, of fixing and repairing bugs and creating new candidates and mutants. Genetic algorithm uh, contains several steps. The first one is it consists of creating, let's say, a simplified representation of the program. It focuses on a manageable version of the program to ease analysis and modification. So here we have to select the part that it will be tested, it will be considered, it will be also then fixed later on. And then we have to select code to change here. So identify specific sections of the code that need modifications or adjustments. And then select the change. We have to choose the type of adjustment to apply to the targeted code. This also will be discussed later on. The two operations that we can use to apply those to create those modifications and to modify our code. And then, of course, we have to evaluate our new program, our candidates. So we have to test the altered program. If all tests pass, what does it mean? It means that we can proceed to the final step. If not, we have to repeat step 2, yes, and then we have to go back to step 2 to select code to change again and again until like we reach a good results and reduce at the end the change to a minimal patch. We have to streamline here the successful change into a minimal efficient patch. This, of course, the goal at the end, to have an efficient candidate that can be used as a modification. Here is the process of genetic programming, and I did not mention it, I think. So genetic algorithm and programming are inspired by biological evolution. APR here, our automated fixing approach, are they are used. This genetic algorithm or programming to automatically generate solutions to software bugs through a process of mutation and selection. So when we say genetic, here we have mutant, we have mutations, and also we have to the steps of selection each time of the part of the code that need to be checked. And so then we combine them to find the best fix and to find the best patch. So as you can see, the process starts with an input program, which is involves selecting initial program, or it can be even set of programs together, so, that will undergo modifications. And then we generate new programs through code mutation and crossover. The goal is to explore a variety of possible solutions that might not be reached by human coders or developers. and to combine elements of two or more selected programs to create a new program. The third step here is the evaluation. It's about evaluating our new candidate and discard if it's highly unsatisfactory and if it's not a good one. And each new program generated is tested against a set of criteria to determine its effectiveness. If a program does not meet the minimum standards or performs poorly in tests, it's discarded. This evaluation step, um, let's say, ensures that only potentially useful programs are kept for further development. And programs that are somewhat satisfactory are taken as input to the step one, so we can use them. Uh, so talking about mutation and crossover, these two operations that are used to improve the program's functionality or to fix bugs by modifying the code. So mutation, the first operation, it changed a specific part of the program's code, focusing on an area highly weighted. uh, what does it mean? Which indicates their criticality, let's say, the impact on the program's execution, the part that has that it's very important in the program. So has highly criticality part number, and then new code introduced during mutation. It's not newly written, this code, but copied from another part of the same program, ensuring that the change remain contextual. And then also, so we have crossover. Crossover, it's about combining two parts from different existing individuals. Uh, so here, generally one of these individuals is always the original program, and here we prioritize mixing parts of the program that are considered most important or highly weighted. To explain maybe better if these are if these are new concepts for you, mutation and crossover, here is like better maybe explanation. We have our initial chromosomes. So as I told you, it's wide matter. It's more known from the genetical science. So for that, here we talk about chromosomes, right? So we have the initial chromosomes. Here we see two sequences of binary digits. Uh, each one represents one chromosome. And these chromosomes in genetic algorithms symbolize potential solution to the problem. Let's say each one has a potential to be the solution of the problem, to fix that problem, to repair that bug. Each byte in a chromosome can represent a feature, or it depends, can be a parameters of the solution, right? So using crossover, the first here part, using crossover, which is a genetic operator, um, used to combine the genetic information of two parents, the first two chromosomes, two parents, to generate new offsprings. So it's analogous to reproduction and biological crossover, right? So um, the son can have things from his father, and others, some characteristics from his father, others from his mother, from her mother's. So here the same thing. So here we have a part from the first chromosome, the second from this second chromosome, and it will be combined in a new chromosome, right? And so this process, let's say, introduces diversity into the population of solution, and it's crucial for the evolution of increasingly effective solution, because we want to create a lot of candidate, in the patch generation candidate, the step two, if you remember the process, the APR process, the step two patch generation, we have to create candidates. Candidates are created from creating mutants, or the mutants are created by using crossover and mutation operations. So this is for crossover. For mutation, it introduces random alterations to the chromosomes, which helps maintain genetic diversity with the population. So in the context of genetic algorithms, mutation can prevent the algorithm from becoming too, uh, how can we say it, too homogeneous and getting stuck at local optima, because we are looking at the end the best candidate, which is the best optimal, right? So in this panel, you can see how certain bytes in the chromosome have flipped, right? From 0 to 1, and from 1 to 0, like here, the third byte, which is changed. And then combination of these two operations, crossover and mutations, allow genetic algorithms to explore a wide range of potential solutions, improving their ability to find optimal or near optimal solutions to complex problems. And in software engineering, particularly in automated program repair, these techniques help generate really robust solutions that can effectively repair bugs in software codes. Means creating a large number of candidates by using crossover and mutates can help developers, as we will evaluate all candidates. We will evaluate the candidates and we will select the optimum one, which can help a lot of developers to, and testers also, of course, to fix those bugs. And so again, here the process starts with the initial set of solutions, and as here represented as a document right here, and each document symbolizes a possible solution, right? Encoded in a format that the algorithm can process. Like, for example, a string of binary digits or whatever. And each solution, as you can see here, is marked with the checks in green, or X or crosses in red, indicating pre-evaluation checks that determine the basics criteria are met for sure. Sorry. So then here is our input, and then our mutate. Our mutate here, as you can see, we have several candidates, several mutants. These are accepted solutions, are subject to mutation and a genetic algorithm operation where random change are made to the solution to introduce variability, right? Using crossover and mutation that was defined previously. And this can involve flipping bytes in a binary string, changing values in a list, or altering any part of the solution code. And then also multiple variants of each solution are created through mutations. And next step, which is evaluate the fitness. And here we will assess how well the solutions solve the problem, or how close they come to an optimal solution. So this is typically a computational process, an equation that should be defined, where each solution is scored based on a predefined criteria. Criteria can change from a team of developers to another. So generally it's defined by manager or developers, and then so can be used to evaluate the fitness and to find the optimal solution. So solution then either discarded into the trash, of course, if they don't do not meet the necessary criteria or move it forward if they qualify. So this step represents the selection phase where only solutions with sufficient fitness scores are kept for further processing. And finally, so one of the mutated solutions is selected as the output because it has the highest fitness score after re-evaluation. And this represents, um, let's say, the end result of this iteration of the algorithm. We will end up with the best solution that has the highest score of the evaluation fitness one. So here, fitness evaluation, talking about fitness evaluation, each modified program or each candidate is assessed uh, by how many predefined test cases it successfully passes. So we have to run test cases and to check if, for example, all tests are passed for this candidate, so it can be considered as one of the best ones. And this measures the program's effectiveness and correctness at the end. So if no program passes all test cases, here we can talk about selection for further modifications. So the one that performs best, meaning it passes the highest number or the most test cases, is selected for further modification. Maybe we can improve it many times. What does it mean? The candidate that is evaluated using fitness evaluation, and then we found that it's not all test cases are passed. Here we can reuse crossover and mutation operations to create a new candidate from this candidate to check again if this can be the optimum solutions or not. And then the final candidate selection here, if a program passes all test cases, it's considered, as I told you, a successful fix for the issue and is selected as a patch candidate. Then this candidate is then passed to a minimizer, which reduces the patch to its simplest form, ensuring it's efficient and devoid unnecessary changes. So this step ensures that only the most effective and optimized modifications are implemented into the final software patch. This is here the last step in the process of APR of fixing bugs means that generally the bug is fixed if we found the optimum solutions. All tests are passed with this new candidate, which is fine. But of course, I want also to talk about software metrics and refactoring, and also software visualization tools that are very important today to improve the quality of the code and to ensure a good quality of the code. So software metrics for those who's the first time that they hear about software metrics. Metrics, it's a quantifiable measures that can be used to measure a specific characteristic in the code, and it can be used in all phases. It can be used even in the requirements phase. We can talk about some metrics in the design. Generally, in the design, we have a set of metrics that need to be used, and then, of course, in the development, which is the part that contains the most number of metrics. So to give you examples of metrics, maybe so when we say a metric, we need numbers. So an example, lines of code. like measuring lines of code line by line. It's a metric. At the end, we can say that our program contains 100 lines of code, right? So it's a metric. This is direct measures. So later on, we talk about and indirect measures. And why we need to quantify, why we need to have numbers, because we have to be subjective and to have subjective information. For example, when the manager asks, okay, um, uh, when you have to finish this program, answering, okay, or I almost there. I still have just few things. Okay, almost there does not mean anything. Doesn't we cannot understand almost there means 1 hour, 1 day, or here in Tunisia, as we say, okay, so almost there means it can be 1 week, right? Almost there. So it's not subjective at all. For that, we need to quantify. When we say, okay, so I need 5 hours to finish, okay, so the manager can understand better now. The same thing for the quality. If we don't measure, means that we don't know if the quality is good or not so good, right? So we have to measure it. We have to use metrics. So as I told you, we can talk about different types of metrics. Can be direct or indirect. Direct means that it's measured directly. We have the information directly. If we apply this, we can have the numbers. Like lines of code, we have metrics of, we have some tools that can help us to measure. We just click on the button and we have, okay, so lines of code in our program. This is very simple, of course, but we can measure the complexity of our code. We can measure coupling and cohesion. We can measure the dependency that goes to our to this method, or it goes from this method. We can many things that can be measured. Number of defects discovered, it can be of course measured also, and it's a number, we quantify it, so it's measurements. Indirect measures here are calculated, not measured. Calculated, there is a difference between measured and calculate. Calculated means that we will use other numbers that are already measured, maybe to have our to calculate this new measurements. Like for example, to calculate to have a module defect density, it need to be calculated. It's not directly measured from the program like lines of code. For example, it's calculated by dividing number of defects discovered by the lines of code or the length of source. Here, using metrics is important to mention that it's challenging. Uh, well, it looks very simple. Having a metric to measure lines of code, why it's challenging? It's simple, you will say. Yes, but you have to know that selecting the adequate metric is challenging because we have a huge number of metrics in the market today. Like lines of code, it looks very simple, but then there is no unanimity about lines of code. Why is that? Because if we write int a in a line and then a new line int b, counting the lines of code, these are 2 lines, right? Another developer has a different practice, which is int a, comma, b, right? Also, it's correct. So here it's counted as 1 line. There is a difference. And then at the end of this lines of code metric, can we say that the program is good or not so good? How we know? It's very difficult. But let's say that it gives us a good indicators about the quality of the code. Of course, having or be based only on one metric is not so good. So it will be better to combine metrics to have at the end idea about the quality of the code. Like for example, measuring lines of code with the complexity, with the coupling, with dependency, we will have a better idea of our code. And we can like we can improve in the future based on this our code. So also in the market there is today several tools that can help us to visualize our applications and to have quickly idea about the quality of our application. Like as you can see here in this figure, here we have rectangles in different formats. Each detail has a meaning here. What does it mean? As you can see, the difference between the small components and large components here, each means that we have small components in our applications, and also we have large components. And here also, so we have more explanation. This for the width metric means the number of attributes that contain the class. The height means the number of methods that contains the class. And then also the colors means the number of lines of code that contains each class. So as you can see here, we have a dark one, means that it contains too many lines of code. And as you can see this, it means that it contains a large number of attributes, but not for the methods, but not large number of methods. More the color is dark, more we say that it contains lines of code. Lines of code, it's a good indicator, guys, because it gives us idea about our program, taking into consideration also the number of methods and attributes here. We can have also idea about the average of lines of code per methods, so we can have idea if the code is complex or not. And of course, if it's complex means it's not maintainable. If it's not maintainable, it's difficult to fix and to repair the bugs at the end, right? So for that, this why I'm talking about this visualization tool and about metrics, because today it's better to prevent and to predict than to fix bugs. Fixing bugs is possible with the process that I showed you, creating candidates, trying to fix bugs, but here it's better to use this. These tools are very easy to use, so it will be good if you have the habit to use these tools. If you use Eclipse, for example, as a plugin, you have metrics plugin that you can download it and you can upload it. You can use it on Eclipse. Also, so for visualization tools, many visualization tools that exist on the market. Another tool that can show us that can give us idea about the quality of the code and show us our code, if it's complex, if it's not, if we have large component or not. So as you can see here, we have few large component and then small. The majority are very small. The same thing with another tool here. A huge number of small components and then others that are more huge with different colors. And again, colors and size are important in this kind of tools. Also, so this can detect what we call anti-patterns, right? Because if we detect that we have a huge component like this ones in our applications, a huge methods in our, or a huge class in our program, huge class, what does it mean? It means it's a God class. God, God class is an anti-pattern. Also, it's known as it's called God or Blab class. And this what we call bad smells in the code. Bad smells should be detected earlier to not have at the end bugs, to not reach the step of failures where we, as I showed you at the beginning of this presentation, historical failures can be avoided, and from the beginning, having a good practices and the best practices used is much better than like fixing bugs. And also, so refactoring, which is very known activity, means that we will refactor the code without adding a new functionality, but just we will improve it. Like here, if I go back here, if I detect that there is GAD class like this one's two big classes with a large number of methods, it will be better to split the method into two methods, for example, or to split the class into two classes. If, for example, a class contains 50 methods, 100 methods, it will be better to divide it into several classes, thinking um, about design principles, which is each class has a single responsibility. So of course we have to split those ones, these biggest ones, into parts, into more than one class by using refactoring. So we have here we have to think about refactoring each time when we detect using metrics or using visualization tools anti-patterns, so we can like uh, we can split and improve the quality. But I just give you an example, of course, of an anti-pattern of a GAD class, but we have a huge list of anti-patterns that need to be detected and fixed. And then each time, don't forget also to evaluate after modifying your application, to evaluate it. Don't evaluate it at the end. Try evaluate it each time, because if you evaluate it at the end, maybe it will be a mess. It will be a problem to fix the problem. The idea is to restructure, to evaluate, just to be sure that it works fine, and then you can add more operations. Sorry, this is it. And if you have questions, thank you for listening. And I'm happy to answer to your questions, of course.
Okay, thank you very much for the excellent presentation, Prof. Hamza.
Thank you.
Prof. Hamza, I hope we can collaborate on research project in the future.
Very
I'm
good.
waiting for that.
Nice. I would be happy, as I told you, I would be really happy to collaborate and to continue in this field of projects, or also even in new fields. So to let you know that here I'm talking about genetic algorithms, but also today we use machine learning, and we use other also techniques. So we can, of course, collaborate with pleasure.
Okay. Maybe now we would like to open time for question from our participant. If you have any
Yes.
question, please feel free to type them in the chat box or raise your hand. Okay. Maybe Rifan, please. Okay. Wait for it.
Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Waalaikumsalam.
Hello, ma'am. Good evening. Introduce myself, Arifan. I am a student at Bandung Teknologi University. Sorry, ma'am, I can use the camera because my network is better. My question, how do mutation and crossover help improve the performance and adaptability of programming software? Thank you.
Rifan bisa diulang pertanyaannya, kayaknya kurang jelas,
Okay.
atau bisa di chat room
Okay.
nanti, saya yang baca.
Okay, my question, how do mutations and crossover help improve the performance and adaptability of software programs?
Sorry again, can you repeat, please? I did not.
Okay. Maybe Rifan said, wait. Tadi yang tentang mutasi ya, Rifan ya?
How do mutations, Rifan, right? How do mutations and the crossovers help improve the performance and adaptability of software programs? Yes, okay, so good question. So here, mutations and the crossovers are used as two operations of genetic algorithm to create new candidates. But we are not sure that these new candidates are good or not so good. We have to evaluate them, but it helps us to create and to generate, let's say, a huge number of candidates. We can create like thousands of candidates, and automatically we can evaluate each candidate to check if it can passes all our test cases that are defined or not. So the idea of crossover of mutation is just to create candidates. And then those candidates will be tested and evaluated, and then so we can ensure if they can, if are performant or not. So it's about performance and adaptability also, if you answer well in your to your questions. Means it's about creating candidates. A candidate, I mean by candidate, a program that is different to the initial one. It can be, we can have a small difference, like as I show you in the example, a byte that is changed from 0 to 1, and then we consider as a new candidate. Is it clear?
Oke, Rifan, apa sudah cukup? Sudah
Okay,
clear?
Miss. Okay, Miss. Thank you very much.
Thank you.
Okay. Prof.
Also,
Hamza, one of participants inserting question on chat room.
Yes.
Chandra Isan. On what basis is we say the software or a method is good or bad? Is there any guidance? Like for example, for main 100 lines is bad.
Excellent question also. So here talking about metrics, when I said we have to measure the quality of the code, to measure the lines of code, and then it's one of the challenges to judge if this number is good or not so good, because as you mentioned here, Ihsan, that okay, 1,000 lines, is it good or bad? So here, defining the threshold is challenging, and generally these thresholds are defined by experts internally in the company. Each company has its specific threshold. Like one, for example, one of the companies say, okay, so the threshold that we should not surpass is, for example, 500 lines of code. What does it mean? It means when we measure, if we found 1,000 lines, so it's bad. Another company, so it's really internally defined by managers. There is until today no research paper can or capable to define the exact number of this threshold. Right. So for that, it's difficult and it's challenging, and one of the challenges. So so it's an excellent question. It's very challenging to answer if it's good or bad. Even the complexity or dependency. If a class has dependency with 50 other classes, okay, so is it too much or it's fine? How can we know? It's defined by managers. internally in the companies.
Thank you. Okay, another question. Maybe Agnes, please inserting
Okay.
question.
Okay, thank you for the opportunity and good evening, Miss. Let me introduce myself. My name is Agnes. I come from Industrial Engineering Department, class 21. And here I want to ask about what role do genetic operators such as crossover and mutation play in the effectiveness of genetic programming?
Okay. Prof. Hamza, the question is what role do genetic operators like crossover and mutation play in the effectiveness on genetic programming?
Okay, so what are the benefits, right, of these operations and for use it, right, for repairing and fixing bugs? So for the benefits is to create as much candidates, to create as much programs as possible in a short time, and then those will be created automatically using tools, and at the end it will be also, those will be evaluated automatically. It means that here we are talking, we talk more about an automated process than a manual process, and which can help us to improve and to fix the bug automatically. So the whole process is automated, starting from detecting the bug to fixing that bug using crossover and mutations. So I repeat, we have to automate the process using crossover and mutation. Crossover and mutation is used to create several programs, several, let's say, versions of our initial version. So we can create different versions, and then it will be evaluated using fitness evaluation.
Okay, thank you. Another question, Zamzam. One raise hand, please.
Thank you, Bu. Hello, Mr. My name is
Hello.
I'm from Universitas Teknologi Bandung. Permission to ask, Mr. What are some effective strategies in fixing hard to track bugs, gitu, Mas? Thank you.
Thank you. It's about tracking bugs, right?
Tracking bugs.
Yes, strategies for tracking bugs, Prof. Hamza.
Tracking bugs. Yes, good. Very good. So we can track bugs using also today several tools that exist like Jira to track bugs and to be able to report that bugs. So each time when we detect that bug, we can like assign it and open in Jira a file where we can choose the status of the bug. We can so as you know, the bug has a life cycle, right? So we can choose the status. We can assign the developer who can fix that bug, and then we can check each time if it's validated, if it's fixed or validated or not. So here, this can be used using like tools like Jira, as I told you. And then the process of APR is in the part of when we try to detect and fix the bug. But tracking is used generally manually by humans to report that bug and to assign it to someone else if it's not fixed automatically. So Jira here, it works fine to track bugs.
Okay, thank
Okay,
you.
thank you, Mr.
Thank you. Welcome. Also, I think on the chat we have some questions, right?
Yes, in
Uh,
chat room, Prof. Hamza, how machine learning and AI can be applied to enhance the bug
enhance the bug.
detection and repair process? Are there any current limitation or challenge with using this technology?
Also, yes, excellent question here. So machine learning and AI can be applied. Yes, instead of genetic algorithms, we can apply machine learning and AI. Even we can combine between machine learning and AI and genetic algorithm today. So how can we use machine learning? For example, using historical data. An idea here is to collect a lot of historical data, a lot of historical bugs that are reported, for example, from Jira, and then these are considered to train the model, right? So we try to train the model using historical data, and then we will try to use the model to fix automatically based on the data that was based on the historical data that was used to learn the model. And then, so of course, we can evaluate our model. This also is a good research area that every day we have new papers, new research papers on this part about the robustness of models, about the technique used, about the data collected. But good to know that to have a good accuracy of the model, we need at the beginning to have a good number of data collected, which is not easy today to collect a huge data, but it can be also automated. We can like create scripts to extract data and then to be used as inputs of our models. So this is how we can use machine learning, for example. Yes.
Okay, that is clear. Maybe the last question from Chandra Isan asks again, when APR repairing our code, does the APR will using this solution or just use first accepted solution? How it affecting our software quality?
Okay, good. No, it's not about yeah, good question. It's not about selecting the first accepted solution. We have to evaluate the whole solutions, and then we try to find the best one, the one that is optimum or close to the optimum, right? So the best, and then also, so here we can have different approaches, but the approach that give us the best results is to compare between different results, right? Compare between different results, and then we can like select the most robust one that can be considered as the optimum result. Good.
Yeah. In question in chat room again. Could you explain in a simple or analogical way how bugs work? I'm sorry for asking this because I'm not from the IT-based student, but the past bugs in something that interests me from
Okay.
Alam.
Sure, no problem. So a bug means a fault. When the developer develop a code, it's possibly that he made some errors, right? A mistake. That become a bug when we can visualize it. A bug or the fault can become a failure at the end if, for example, we execute the program. We execute it, we found that what we expect is different to what we have, means it's a failure. Like the problem at the beginning when I present TERAC 25, I present also Ariane 5 rocket, Ariane 5, also Log4j vulnerability. All these are failures because there is before bugs, because there is before also mistakes. So again, a bug is a fault in the program, something that is wrong in the program. Like if, for example, developer, instead of writing int a equal 10, he wrote int a equal 20. So what we want is 10, he wrote 20. So here we talk about an error. When it's visualized and detected, it's a bug, and it becomes a failure if we change the expected behavior of the program. Be careful here. Not all bugs are failures at the end. Sometimes, and many times it happens, we have the bug and the scenario to detect the bug was not run. So it's not a failure, right? But it's still a bug.
And that is clear, maybe.
Please don't hesitate if it's not clear. I can for the student, I can repeat, or I can maybe explain better with more examples.
Yeah. Yeah. Maybe that is clear, Prof. Hamza. Prof. Hamza, maybe I can send you message for pacar collaboration.
Sure, with pleasure, sure. And him, I don't know if you can see my screen. Stop shared. Here, I can give you my email address. So if you want, you can share screen.
Oh, yeah,
Yes.
maybe you can share screen or
Yes. Here, it is my email
send
address.
in chat room or to
Yes.
me. Oh, okay.
Can you see it?
I write.
Okay. So it's a pleasure to collaborate on these fields or other fields also. So I work um, on the field of detecting, so predicting vulnerabilities. Also, so on UX design, we have interesting like research things that we are doing actually on UX, on user experience. And don't hesitate, please, for everyone, for all students, if you want, you can join, or you can like send me an email. I'm happy to answer, to clarify more things if needed, right?
Okay, thank you very much, Prof. Salma Hamza, for an insightful presentation and for taking the time to answer our question.
Thank you so much. With pleasure.
Yeah, let me convey the conclusion of this session. Geometric algorithm and software metrics are essential tools in modern software engineering used to fix bugs and improve code quality. This process involves several stages, including fitness evaluation, mutation, and crossover. Additionally, software metrics provide quantifiable measures for various code characteristics, enabling managers to make data-driven, objective decisions at every phase of software development for requirement development and maintenance. Ya, inti kesimpulan hari ini untuk mahasiswa-mahasiswa dari Indonesia. Jadi algoritma genetika dan metrik ini perangkat lunak yang penting ya dalam perangkat lunak modern yang digunakan untuk memperbaiki bug dan meningkatkan kualitas dari source code yang kita buat. Jadi prosesnya ini melibatkan ada beberapa tahap, termasuk evaluasi, mutasi, dan crossover. Ini fungsinya untuk memastikan keefektifan dari source code yang kita buat gitu ya. Jadi untuk solusi lebih lanjut, apa yang harus kita lakukan, maka kita harus mengatasi bugs dari source code itu. Nah, selain itu, metrik perangkat lunak ini memberikan ukuran yang bisa kita ukur untuk berbagai dari karakteristik source code kita yang memungkinkan kita atau sebagai di manajerial atau organisasi untuk mengambil keputusan berbasis data yang objektif dalam setiap fase pengembangan perangkat lunak dan dari kebutuhan hingga pengembangan dan pemeliharaan. Prof. Hamza, your expertise and knowledge on detecting and repairing bugs in source code have been incredibly valuable to all of us. We appreciate your willingness to share your experience and tips, which will certainly help us in our future projects.
Thank you so much.
Thank you.
Thank you so
Before
much.
we conclude
Yeah.
today's session, we would like to take a group photo with all the participants and our speaker. Everyone, please turn on their camera so we can capture this moment together. We will give everyone a minute to get ready. Oke, semuanya tolong di open kamera. Kita akan mulai untuk pengambilan foto. Yeah, all right, let's get ready for the photo. On the count of 3, everyone please smile. First screen, white. 1, 2, 3, click. Okay. Second screen. 1, 2, 3. Okay. Third screen, white. Okay, fourth screen. Or maybe that is the last screen. Okay, thank you, Prof. Salma Hamza, and our amazing participant for your active involvement today. It has been a pleasure to have you all with us. We hope you to see you again in future. See you,
Thank
Prof.
you. See
Hamza,
you. Bye-bye. Thank you.
participants.
Thank you.
Pak Nasir.
Thank you. Thank you. Goodbye.
Bye.